Okay, so now that we know what inequalities are and how to solve them, let's focus our attention on their solution sets. It turns out the solution sets are a little different, and so we need to take a quick look at that and talk about it and talk about ways to represent them. Now remember what a solution is, right, is the idea is you have to find a value, right, for the variable, and then you're going to sub it in and you get a true statement, right? So that's what it meant to be a solution way back when in chapters, earlier in this chapter, section 2.1 and 2.2. That idea doesn't change. That's still what it means to be a solution. We have to find a value. When I sub it in, it gives us a true statement. And that's basically the same thing that's happening here. Although when we're solving an equation, right, when we get something like x equals 2, that's the only value that makes the equation true. But when I'm solving an inequality, we have a whole bunch of them, right? When we think about this, think of numbers that are to the left of 2 or numbers that are less than 2. Well, we have a whole bunch of them, right? Things like x equals -1 would work. X equals 0 would work. X equals 1 would work. If you want to go a bigger negative number, you can say x is -4. Don't forget about the your fractions, right? So -2/5 would work. So there's a whole bunch of them. So rather than in an equation when only one worked, right, we have a whole bunch. So any one of these, how about I check the -4? If I plugged -4 into the inequality, right, so I found a value, I'm subbing it in, what I should get is a true statement. So -8 plus 3, -5 is less than 7. That is a true statement. So that is one of my solutions. If we put 0 in there, 2 times 0 plus 3 is 7. 3 is less than 7. So that makes it a true statement. So as we're going to see in a moment, and what we're seeing now, is rather than just one value being true, right, we have an entire interval. All right, there's actually an infinite number of solutions. All right, and that is one thing that makes solving inequalities much different. I just don't end up with just one solution. I end up with a bunch of them, a whole bunch of them. Any value of x that satisfies that inequality. So I listed 5 of them. I'm pretty sure you can think of more of them, but any one of those values works. Same thing here, right? We're talking about any value that's less than or equal to 3, right? That's going to work. So the subtle difference here is x can be anything less than 3, like 0 or 1 or 2, right? Or even the negatives, right? -2, -1. But another thing, because we're allowed to be equal to, it could actually be equal to 3 and still work. That's slightly different than what happened over here, right? In this case, we call this a strict inequality. The x's have to be strictly less than 2. So, maybe x is 1.9, or it could be 1.99, or x can be 1.999, but it can never actually equal 2. But in this inequality, right, you can be 2.9, 2.99, 2.999, and then you can all actually be equal to 3. So let's test that. So if I put 3 in there, right, we get a 9 minus 1, and that's an 8, and 8 is at least equal to 8. So it doesn't satisfy the less than part, but it does satisfy the equal to part. So that's a slight difference between those two inequalities, is not only are there an infinite number of things less than 3, but this inequality allows me to actually equal to 3, whereas that one we have to strictly be less than 2. So again, though, we end up with another infinite number of solutions, right? We end up with what we call in math an entire interval. All right, and then even the fractions, right? This one, after we did some work, we get, x has to be larger than or equal to -1/3. So, x can be 0, x can be 1, x could be 1/2, right? X can be 7/4, right? All these numbers I'm giving you satisfy the condition that they are larger than or they are to the right of -1/3. And so, let's just try one of them. Let's put 1 in there. So if I put a 1 into the inequality, what I should get is a true statement. All right, so using my order of operations, we have 2 times 3 minus 1 on that side. 3, well, 1 take away 1 is 0. 6 minus 1, that side's 3. We have 5 is greater than 3, so that's a true statement. So the 1 checks out. 0 would check out. A half would check out. 7/4 would check out. So again, we have an infinite number of solutions. We have an entire interval. All right, and so that is what makes our solution sets. And by the way, one other thing, we cannot be equal to negative 1/3. We have to strictly be greater than. So just like this one here allowed us to be equal to the value that was kind of serving as a boundary, this one we cannot be equal to negative 1/3. We have to strictly be greater than it. So, you know, I think 1/3 is roughly about negative 0.333 with a bar over it. So, you know, something like a negative 0.3 would be a solution. Negative 0.33 would be a solution, right? All these numbers are just to the right of negative 1/3, but you can never actually equal to negative 1/3 because we're not. This is a strict inequality there. All right, so that's some subtleties on the solution sets. Of course, in the because of this subtlety, because there's an infinite number of solutions, it turns out that there's several ways to describe the solution set. So we'll talk about that in our next video.